Sine of x over x without the L'Hopital. Okay, so we are supposed to evaluate the limit as x approaches 0 of sine of x all over x. Okay, so, well, why do we want to calculate this guy without using the L'Hopital's rule? Because, well, there would be absolutely no problem for us to just say that this entire thing, this entire limit, as x approaches 0 of sine of x all over x is equal to just the limit as x approaches 0 of the derivative of the sine of x all over the derivative of x by the L'Hopital's rule. And that would give us that this entire thing is equal to the limit as x approaches 0 of the cosine of x all over 1, where, well, when cosine of x approaches, when x approaches 0, then cosine of x approaches just a 1, so that entire thing would be just 1 over 1, which is a 1. Well, we don't want to do that because this is actually committing so-called circular reasoning. And, well, let me explain that maybe. So, well, we are using the fact that the derivative of the sine of x is the cosine of x using the L'Hopital's rule to solve this particular limit. However, if I were to derive the actual, not the actual. If I were to derive the fact that the derivative of the sine of x is equal to the cosine of x, well, what would I have to do in order to do that? Well, I have to use the definition of the derivative, which is the limit as some tiny change in x approaches 0 of sine evaluated at x plus that slight change in x minus sine of x, and then everything divided by that small nudge in x. Yeah, so that would be sine of x plus dx minus sine of x all over dx. However, now, well, I could use some trig identities to go on and partition this sine of x plus dx so we can do anything with that stuff. So I could rewrite this entire limit as just the limit as dx approaches 0 of, and that would be sine of delta x multiplied by the cosine of x, and then plus the sine of x multiplied by the cosine of delta x, and then everything minus that nice sine of x that was left over, and now we have to divide everything by that delta x. And, well, now we can just kind of go on and partition this entire thing into two limits, because, well, our limit of a sum is the sum of the limits of two limits, and so we can say that, well, I would like to put this stuff into a single limit, and also I would like to put, let's say, this stuff into a single limit, or maybe I'm not gonna be using this column because it's just now it's a little bit better. Yeah, so I want to put that stuff into another limit, so rewrite what. Oh, now it's better. So we write this entire thing. I'm gonna be left with the limit as delta x approaches 0 of, well, the sine of delta x multiplied by the cosine of x all over dx. But now the nice thing is that this cosine of x is just about a constant with respect to the dx, which is the variable that we are taking the limit with respect to, so we can just kind of go on and take it in front of the limit itself, and then we'll be left with, I was supposed to do that in pink, the limit as dx approaches 0 of the sine x cosine of dx minus sine x. So just factor out the sine of x right away. It's gonna be sine of x multiplied by the cosine of dx, and then minus 1 all nicely over dx. And now, as you can see, once again, the sine of x is just about a constant with respect to dx, which is the variable we're taking the limit with respect to, so we can just go on and take it in front of the limit. So what we're gonna be left with after doing all that stuff is, well, here is gonna be cosine of x multiplied by the limit as dx approaches 0, of sine of dx all over dx, and then plus now the sine of x multiplied by the limit as dx approaches 0 of cosine of dx minus 1 all over dx. So we know that, well, now as dx approaches 0, cosine of dx will approach a 1, and so this entire thing is just gonna be 0. Well, that's pretty lovely, because we can just say that this entire sine times the limits is just gonna be 0. And now, well, as you can see, well, we would really like the sine dx over dx to be a 1, so that, well, the derivative of sine of x would end up being a cosine. However, well, what are we supposed to do now? Well, are we supposed to use the L'Hopital's rule here? Are we supposed to take the derivative of sine of dx with respect to the x whilst we are literally trying to derive the derivative of sine x? Well, that doesn't really make sense to me. So we do have to find another way to calculate this limit, and I would like to show you this way, guys, in this video. So let's get right to it. The proof is going to be conducted kind of piecewise. So first of all, I would like to find the limit as x approaches 0 from the above, from the positive x direction, of the sine of x all over x. You probably have already guessed what I'm going to be taking the limit of, yeah. So that's the thing. And well, how am I supposed to achieve that? Well, I would like to show you guys a pretty lovely geometric proof. So I would like to draw myself a coordinate system, and now draw a quarter circle, a quarter of a unit circle. I'm only going to be covering a quarter of the unit circle, not the entire one, because, well, as x approaches 0 from the above, I will only actually care about the values between pi over 2 and a 0. I mean the angles in radians that are close to 0, so only the first quadrant. So I just say that, well, x is between 0 and pi over 2. And also I would like to say that it's in radians. That's going to be pretty important in terms of what I'm going to be doing later on. So, well, this is not quite a unit circle, but now it's, I think, better. I think it's better. Yes, so that is supposed to be a unit circle, and so here we've got the point 1, 0. Here we have the point 0, 1. Awesome. Let's maybe draw something like this. There's gonna be our radius as well. There's gonna be our angle x. And now, I would like to draw myself a line segment that will connect those 2 points of, let's say, connection of those radiuses. Those radii to the circle, yeah. And I would like to calculate the area of this triangle I have right over there. Well, this area is gonna be what? Well, I don't really have a height or the base here, because I have no, like a right angle here or here in the triangle. So I will have to use a trigonometric formula for the, how do you say it? The area of the triangle. But the nice thing is that those two, and I want to take the purple, those 2 line segments are of length 1, and we have an angle of x lying between them, and so we can use the formula that this area is gonna be equal to 1/2 multiplied by 1 multiplied by 1, so I'll just say 1, I'm not even writing it down, times the sine of x. Pretty lovely. Now I would like to calculate the area of, well, once again, this entire segment. However, this time I would like to include this area right over here, this small arc that, well, looks like it's not even there, but it is there actually, yeah. So, well, as you can see, this new area, this orange area, is gonna be greater. It's gonna be definitely greater than the purple area. And so what's gonna be the measure of this orange area? Well, this is gonna be, because x is in radians, a half multiplied by by the radius squared, but radius squared is just nicely a 1, and then multiplied by the measure of x in radians, so it's going to be just 1/2 of x. Lovely. Now I would like to take myself a third, oh no, there's gonna be the second line segment here. That's gonna kind of appear out of the blue, but well, whatever. And I would like this guy to be tangent to my circle at the point 1, 0. I would like to extend it only this far, that I can just extend this radius and make those two connect, yeah, something like this. And I would like to calculate the area of this entire big triangle, yeah. So, well, how can I do it? I can't really use the, one half, one half the side length, sine x kind of stuff, because I have no idea what this guy's measure here, what this line segment's measure is. But, well, I have a right angle here, because, this is a radius and this is a tangent line to the circle, and so the radius and the tangent line always are not parallel. They are the straight angle to each other, no, the right angle to each other. So, well, I can just do the 1/2 base times height of this triangle as the area. So, well, that's gonna be this guy right here is gonna be the height, and that's gonna be the base. So, well, I know the base already. It's just one. It's just a radius. It's just the radius. But what's gonna be the measure of this tangent line, of this yellow line segment? Well, we see that basically the tangent of x will be equal to this yellow line segment. I don't know, it's denoted as the question mark divided by 1, which is another adjacent, which is the adjacent. That's the opposite, that's the adjacent, that's the hypotenuse. Am I right? I hope I'm right. I'm not really good at English stuff. Yeah. So we see that the length of this line segment is going to be just the tangent of x. It's going to be just the tangent of x, which is absolutely perfect, because now we can see that this area of this entire, of all of those areas plus this yellow guy is just going to be equal to 1/2, well, tangent of x times 1, that's just tangent of x. However, the nice thing is that we now see that, well, the purple area, so maybe I wrote it right here, 1/2 the sine of x is going to be less than, well, the area of the purple stuff plus the orange area, which is a half of x itself, and then the sum of all of the areas also with the yellow area, which is 1/2 tangent of x. We have this kind of an inequality set. You have the set of inequalities. But now what we can do here is, well, first of all, cancel out those halves. Yeah, that's probably something I would like to do here. Yes, I'm gonna get rid of those. And now what I would like to do is, well, kind of invert everything here. I would like to invert all of those guys. So I would like to take the reciprocals of everybody here. And maybe I'll just settle on one color, for God's sake, because it's too much of a struggle to to change it all the time. So it's gonna be 1 over sine x is greater than the reciprocal of x is greater than, well, the reciprocal of the tangent is cotangent, but that's just the cosine of x over sine of x. And I think you know what I'm getting at right now. I can just go on and multiply everybody by the sine of x right now in order to, get sine of x over x here in the middle part of this set of inequalities. That's gonna give me that one is actually greater, or maybe I'll say greater than or equal to, because I'm only going with those functions, so those strict inequalities don't really have to occur. There's gonna be 1 greater than or equal to sine of x all over x, which is greater than or equal to just the cosine of x. But now I can just kind of go on and take the limit of everything, right, of everybody right there, which will nicely give me 1 being greater than or equal to the limit as x approaches 0 from above of sine x all over x, which is greater than or equal to the limit as x approaches 0 from above of the cosine of x. But now, well, I didn't even write the limit here in front of the 1, because the limit as x approaches 0 of 1 is just a 1, so I don't really care about it. But now, well, this is the limit we're looking for. And what is the limit as x approaches 0 from the above of cosine of x? Well, this thing is just a 1. And so what we end up with is that 1 is greater than or equal to the limit we were looking for, sine of x all over x, which is greater than or equal to 1. And so, well, I wanted to say by the squeeze theorem, but honestly by just logic, we get that our limit we're looking for, well, if it's both less than or equal to 1 and greater than or equal to 1 at the same time, it has to be equal to 1. And the proof for, well, x approaching 0 from the negative side, so this thing right now, will be just about analogous, so I'll leave it as an exercise for you guys. So, you know, let's maybe go once again over what we did here in this problem, yeah? So we're supposed to calculate this limit as x approaches 0 of sine of x all over x without using the L'Hopital's rule, because we saw that this thing right there, using the L'Hopital's rule to solve this problem, is just a circular reasoning, given, well, how we actually derive the derivative of the sine of x, which is the cosine of x. And then what we did is we just drew a quarter of a unit circle in the coordinate system, and then ended up, after calculating some out of the blue areas, that we ended up with this beautiful set of inequalities, which actually yielded us, after taking the limit of it, that our limit we were looking for is between 1 and 1, which means that it just has to be equal to 1. And then I left the other easy part of the proof to you guys as an exercise. Awesome, so I hope you guys enjoyed this video. Well, if you did, this is the next one, and